Hi, let's talk about the metric system. You might have heard that the United States doesn't officially use the metric system. And although that's true that the US government doesn't officially use the metric system, use of the metric system is very widespread in the United States. In fact, in medicine, it's almost 100% the metric system so as a consumer of the medical system, any medications you get are going to be in the metric system. They're going to be in milligrams or milliliters or micrograms. So we'll talk about those units. If you get weighed now, they either weigh you in kilograms or they're going to convert it to kilograms before they put it in your chart. All of science in the US uses the metric system, and this has been true for decades because it's international scientific publications are in the metric system. So US scientists have been using the metric system almost exclusively for decades. Manufacturing in the US is also working its way towards it's getting there. It's getting there, and it's increasing every year. Talking to someone I know who owns a small parts manufacturing company, about 50% of their orders are currently in metric system units, and it's working our way. So even though the US government doesn't officially use the metric system, we're getting there. Oh, and NASA has completely converted to the metric system about 20 years ago after they crashed a multi-million-dollar Mars probe because somebody didn't convert units correctly, and the Mars probe had parts that were in imperial units and parts that were in metric units, and somebody didn't do the conversions correctly, and it caused the loss of a multi-year project. So NASA is now completely on the metric system. So even though we don't officially use the metric system, it's very widespread and definitely to your advantage to know it, even if it's only as a consumer of the medical field, as a patient. If you're going into medicine as a profession, as a nurse or a doctor or whatever, you're going to be using the metric system at work almost exclusively. So in the metric system, we have four basic units of measurement. We have for length, we have meters represented by a lowercase m. We have G for grams. We have, let's see, weight, grams, volume, liters, which we use a capital L. Normally for these basic units, we use a lowercase letter, but because the lowercase L and the number 1 are confused, especially in the US because we write them both exactly the same, we use a capital L for liters. And then there's also for temperature, degrees Celsius or centigrade, and those are exactly the same thing. So the most important units in the metric system, as it has been used now for a little over 150 years, are the jumps of 1,000. So you probably, when you learned the metric system in middle school and high school, whenever you learned it in school, you probably learned all these intermediate units that are jumps of 10 that are basically useless, that no one uses, like decameters and decimeters and hectograms, and nobody uses those units. And I think it's useless to teach people those units, and it just makes people hate the metric system. So let's just focus on the units that people actually use. So for meters, 1,000 meters is a kilometer, so that's useful. 1,000th of a meter is a millimeter. So, and we're going to reuse these same prefixes for all of the units. So the lowercase m means milli, and that's 1,000th. So there are 1,000 millimeters in a meter. So if that's our 1 here, so that's 1,000 of them. and millimeter is 1/1000th of that. Now in science, especially in biology, we use one smaller unit. And if we were in the lab, we would be using these micro units. We use a Greek letter, a lowercase mu for this. And it looks sort of like an M, but with points instead of humps. So this letter here, this is the Greek letter mu. It's lowercase mu, Greek letter mu. The capital mu looks just like our capital M, but that's the lowercase mu. And this is 1/1,000,000th of a meter, or 1/1000th of a millimeter. So these are all jumps of 1,000. And the only exception for meters that sometimes gets used is centimeters. Because if you're measuring everyday household objects, a meter is really big. A meter's about a yard, and a millimeter is really small. So it's kind of useful to have one in between. So a centimeter gets used a lot as well, and that's 1/100th of a meter. So there's 100 centimeters in a meter. So that's an intermediate unit that's not a jump of 1,000 that actually gets used quite a bit. Okay, so for grams, 1,000 grams is a kilogram. 1/1000th of a gram is a milligram, and that should look very familiar because that's on medicine packages. Medicine is often in milligrams, and then, or micrograms. So a microgram is 1/1000th of a gram. And some of these units have nicknames because they're so long to say. So milligram is often pronounced migs or megs. So if you're going to weigh something in the lab, somebody might say, you know, weigh out 100 megs of this. So it's got a nickname instead of saying milligram all the time. For liters, kiloliter, isn't common in everyday usage, but you would see that in a scientific paper that's talking about large volumes of water or something. Milliliter, we would have used this very extensively in the lab, if we were in the lab. And then microliter, which is a very small unit. We would have also used microliters in the lab for our DNA labs if we were in the lab. And these as well have nicknames. So milliliter is often pronounced mils, instead of saying milliliter. So if you're talking about a concentration of something that's milligrams per milliliter, you might say, oh, the concentration of that is 10 mgs per mil. So those have little shorthand nicknames. Oh, and this one has a nickname too. Way before the metric system was common and micrometer wasn't being used that expansively, it had the nickname of micron, which was very useful for measuring the size of specimens under the microscope. Although the term micron is kind of becoming old-fashioned as more and more people just use micrometer for that. So, but if you hear micron, that's what that is. And for temperature here, now, you'll notice that on the quiz that I'm giving you, there are no conversions between metric units and imperial units. I'm not going to ask you to figure out how many centimeters are in a foot or something, because if we're using the metric system, we're just using it. Why would we want to convert things back and forth between the imperial units? We just never would. Only historians are going to be doing that a few decades from now. And the same is true for the Celsius temperature scale. I'm not going to ask you to convert temperatures back and forth if we're using Celsius, which you will at work if you work in a science lab or if you work in the medical field. And if you pretty much go to most other countries in the world, they don't use the Fahrenheit scale, they use Celsius. So, but instead of trying to constantly convert things back and forth, just get used to this, to Celsius. And if you just know 4 different temperatures, you can pretty much figure out whether water is at a dangerous temperature in the lab, whether you need to wear a coat outside, And those four temperatures are the temperature at which water freezes, the temperature, room temperature. You know, what's your typical comfortable indoor room temperature? Human body temperature, and boiling of water. So these are, and boiling and freezing of water at sea level, pure water at sea level, are the basis for the Celsius temperature scale. Now, what is the basis for Fahrenheit? We're not 100% sure, but people have hypothesized that 100 degrees Fahrenheit was supposed to be human body temperature, and he was a little bit off because it's suspiciously close to human body temperature. And 0 was the coldest that Fahrenheit could get it in his lab with the primitive refrigeration equipment that he had in the 1700s, or in the, not 1700s, 1800s. So, but we don't really know what the Fahrenheit scale was based on. So freezing in Celsius is 0. Room temperature is, and this varies culturally and by part of this country and also around the world, but in the United States, comfortable room temperature is usually 20 to 22 degrees. And you know, I've been places where a comfortable room temperature is considered to be much cooler, like 16 degrees, or warmer, like 28 degrees, depending on where you are in the world. Now, human body temperature is not a single number. You probably have heard before, you know, in Fahrenheit, the human body temperature is 98.6. Well, in fact, that's not the case. Your own body temperature varies by approximately a whole degree Celsius during a single day. So our body temperature is a range, and normal human body temperature ranges from 36 to 38 approximately. Children tend to be a little hotter. Old people tend to be a little bit cooler. And if you're going to grow bacteria in the lab that normally live in the human body, you would have your incubator set for 37.5 degrees Celsius. So that's the range for human body temperature. So if you're going to go outside and you're in a hotel somewhere, anywhere else in the world, and the radio says, or your internet says that the temperature outside is 40 degrees, well, that's pretty hot. That's warmer than human body temperature. So you know it's going to be a hot day. If the temperature outside is 5 degrees, you could say, well, that's pretty cold, but it's above freezing. So, I'll wear a coat, but it's not going to be terrible outside. The boiling temperature is 100 for water. So if we have a hot water bath set in the lab that's 60 degrees, it says 60 degrees on it, that's hot. That's going to scald you if you put your hand in it. If we have a hot water bath that's set for 80 degrees, you should be very cautious and not let that water touch your bare skin. So that's how you can use these four numbers to determine how careful you should be with various temperatures of things in the lab. If something in the lab is 20 degrees, you don't have to take any precautions at all. It's not even going to be that cold. That's going to be room temperature. So let's talk about some conversions now. So you probably learned to do these conversions either to use a formula or to use stoichiometry. So let's look at the first one here, 3,000 meters, converting it to kilometers. Now you probably learned if we're going to do it by stoichiometry, we would take the number given, 3,000 meters, put it over 1, and then we want meters to cancel out and replace it with kilometers. So we need a relationship between these two units. So we would say there's 1,000 meters in 1 kilometer. Meters cancels, and then we can put the numerators and denominators together. So that gives us 3,000 kilometers over 1,000. And then when we divide this, we get 3. So that's the long way to do it, and this works. Stoichiometry with the canceling of units that works. It always works, but it's a lot of writing and it takes a long time. So let me show you a shorter way to do it that's much faster and doesn't require writing anything out like this. So, and I've been using this method for so long, I can't even remember how I learned this method. I can't remember if I thought of it myself or if somebody taught me. Probably somebody taught me how to do it this way, and I just have no memory of that whatsoever. So what you need to know, the good thing about the decimal system, the metric system, is that you can do conversions to different units by just moving the decimal, which makes it a lot easier than trying to figure out how many ounces is in a quart or how many inches is in a mile. There, you know, it's always a weird number. But with the metric system, it's just moving the decimal place. So what you need to know is which way to move the decimal place and how many places to move it. So if it's a jump of 1,000, like meters to kilometers is a jump of 1,000. So if it's a jump of 1,000, then you're going to move it 3 places. If it's a jump of, if it's 2 jumps of 1,000, so 2 jumps of 1,000, then you're going to move it 6 places. And that would be, for example, if instead of meters to kilometers, if we were doing millimeters to kilometers, that's 2 jumps of 1,000. So how do you decide which way you're going to move that decimal? And if you don't see the decimal, it's at the end of the last number. So that's why I stuck the decimals right there. So look at your units. The number is going to do the opposite of whatever the unit is doing. So in this case, the unit's getting larger. So if the unit gets larger, the number gets smaller. So that tells us which way to move the decimal. So we're going to be moving this decimal to make this number smaller, which is this way. That's the way we're going to be moving the decimal. So unit gets larger, number's going to get smaller. So how many places do we move it? It's a jump of 1,000. We're going to move it 3. So 1, 2, 3, 3 kilometers. And we didn't have to write out all that equation. Okay, let's look at the next one here. So here, the unit gets smaller, and it's 2 jumps of 1,000, right? It's microliters. Liters to microliters. Milliliters is in between here, and we're not going to convert to that. So that means we're going to move it 6 places. Unit gets smaller, so the number's going to get larger. So that means that decimal is going this way. So we're going to go 1, 2, 3, 1, 2, 3. So 400. We moved it 6 places. And let's look at the last example here. There's our decimal. Our units are getting smaller, so the number's going to get larger. So that means the decimal's going that way. Number's going to get larger, and this is a jump of 1,000 again. So jump of 1,000, we're going to move it 3 places. So 1, 2, 3, 70. So and I like to put that in there so we don't mistake it for a number 1. Okay, so those are our sample problems. You're not going to be doing any conversions with temperature. But you'll see on the quiz that there are some conversions there. And look closely for that mu. So when I drew it, you know, I kind of drew it like that. And if you're writing mu, make sure that there's points on the top and not humps. If you draw it like that or like that, that is going to be milli. That is not going to be micro. So mu means micro, and that means it's 1/1,000,000th of whatever the original unit is. So a microliter is 1/1,000,000th of a liter. Okay, so go ahead and do the quiz, and if you have any questions, we'll talk about it in discussion section.